Well, here we are at section 3.2, methods of or measures of dispersion. That means how widespread your data are, from first to last item of data. First of all, an easy one, range. If you want the range, all you need to do is take the maximum value, subtract the minimum value, you know how widespread your data are. Very easy. You can do that for one thing by arranging your data from smallest to largest or largest to smallest, either way. You can actually do one variable statistics on your calculator, and that'll give you a max and a minimum value. Subtract those, you got your range. So here's some examples. I'm going to ask you to stop occasionally and give it a shot of your own. So these are two different problems. So for the ones on row A, put those into your calculator. Hit stat, calculate one variable statistics. You can get your maximum and minimum value, and then subtract the two, you've got your range. Give those a shot, pause for right now, come back when you've got those two answers, and we'll see what you got. Here we've got the answers. Did you get 42 minutes for each one? If you did, congratulations. If you had some trouble, see me in class. Next, the variance. This isn't seen very often, whether it's population variance or sample variance. It has some issues. It's a good number for seeing how much your data vary. However, your calculator, for one, doesn't give you variance directly. You have to find the standard deviation, or the appropriate one, either population or sample, and square it to get the actual variance. Remember, the population variance and the sample variance, just a little bit different. And just for the record, take a look at the denominator for both of them. They're both set up almost exactly the same. Mu and x bar are the same, but the denominator is different. For the variance of the sample, there's a denominator of n minus 1. Sample size minus 1, and that's an adjustment because it is a sample and it's not for the whole population. That's enough said for now. When you're calculating the variance and various other things as well, we're on to one more decimal place. So if you've got whole numbers, for example, give the variance with one decimal place after your number. However, if you're using currency, stick to 2 decimal places. That's a special case. Next, as is usually the case, if you're working with a population, you're also noting that with a Greek letter. If you're using a sample, you're using one of our standard letters, like S. Here's an example. 3, 2, 5, 6, 4 are the numbers that you're given for the number of rides. What you're asked to do is find the variance. So, since this is a sample, you're going to put those numbers in your calculator. Let's say you put them in L1, then you do one variable, stats, using L1, and since it's a sample, you'll be looking for this value right here. Take that value. This is the standard deviation for the sample. That's not what you want for this one. You'll need to square it. If you ask me in class, I'll tell you a sneaky way of getting that. The straightforward way, perhaps, is to just look at it on your calculator, write it down on a scrap piece of paper, write it in your calculator, hit squared, and you've got your variance. If you're using Excel, here are the two formulas you use. This one for the sample, this one for the population. Pretty simple. And that's how the calculations goes. And I don't know about you, but I'm doing the just cross that off of my list of things to do. I'm going to use the calculator or Excel, but actually I'm going to use the calculator because it's easy. But Excel is not hard at all, as you saw on the previous slide. This is how you do it longhand. I don't know why anyone would even suggest you do that. My apologies to anyone who does it this way in class. This is not what I do. And there are a lot of other instructors that stick with the technology. What you're here for, as far as I'm concerned, is to learn about statistics, not how to crunch numbers manually. Moving on. More calculations. You don't need to do that. Technology tip, do it using Excel or TI-84, whatever you've got, TI-Inspire. Some of you have TI-Inspires. Fantastic. Now, for the standard deviation, that's one that you're going to get directly. Remember, for the population standard deviation, it's a Greek letter. For the sample, it's a regular letter like we would see in our books. Again, when calculating that standard deviation, what should you report? One more decimal place than what you've got in your data. Look at your data. How many decimal places? The largest number of decimal places. Add 1 to that. That's what you're going to report for your standard deviation, variance, or whatever it is. Again, Greek letters for population, regular letters for sample. Definition. This is how the standard deviation is calculated. All you need to know, as far as I'm concerned, when it comes to calculations, this is how your calculator does it, or how Excel does it. You're not going to do all this. Did I do it when I took statistics when I was 19 years old? Yes. There were no electronic calculators, so I'm dating myself. And it took a lot of effort because every data item had the mean subtracted from it and squared. You did that for every single data item, added them all up, that's what the sigma means, divided by how many data items you had, then took the square root at the end. And hope you don't make any simple mistakes. Next, here's a data set. Use this, take this data, put in L1 or wherever you like, and find one variable stats, telling the calculator, make sure you look at list 1, and since we've got every patient, that means we're looking for sigma of x, because we're talking about the population, every patient, not a sample of the patients. So do that, see what you get for this, and after you're finished with your pause, move along. And here we go. That's how you could do it. I'm not sure why you would ever want to do that. You can see how many calculations you have to do. Each one of those data items, individual data items, these, have the mean subtracted from them. That gives you this. And then you square this to get that item. And then you take each one of those, add them all together, take your sum, you divide by n, and then you take a square root. It doesn't sound like a whole lot of fun, does it? And that's what it would look like if you take it step by step. However, what I expect you to do is use the TIA4 3 or plus. Do it that way. Here's your stat. Put the numbers in. Go back to stat. Calculate one variable stats. Tell it which list it's in. And then look for sigma of x. And you should get 15.2 if you've done it correctly. If you have some trouble, send me an email, tell me or show me exactly what you did, and I'll get you back on track. One-to-one probably is the best idea because I can see you putting stuff in the calculator. The only thing I have to ask is, if you do, don't do it at triple speed where I can't see what keys you're hitting as you go through it. So there's a technology tip, which was on the previous one. That's what it should look like when you hit the one variable stats. And this is the one you're looking for because you were working with every patient alias population. Make sure your frequency is 1. Make sure your data is an L1 or wherever you want to. You can put in one of the others. In fact, I encourage you to try some different list occasionally, just so you don't get locked into using L1 all the time. Here's a question for you. We've got 2 different companies, and we're thinking Mark is considering investing into the stock market. He sees the standard deviations for the daily stock closing prices for pro facto and for Yardsmith. So, what do these standard deviations tell you? Okay? Remember, standard deviation. So as the stock prices go from one day to the next day, to the next day, to the next day, and so on, if you take those stock prices and calculate the standard deviation for each one, these are what you get. What does that mean? Pause, give it a little bit of thought, because this is something important. This is something you could actually end up doing. If it's not stock prices, it might be something else. But the standard deviations could tell you a story. And here is the story. I'm not going to read this for you. Hit pause, read through the whole thing. If you have any questions, send them on to me. Make sure if you have a question, you send a screenshot of this and what you think it is and what the answer said it was, and ask me how you got off track. So this is a way to do it with the Hawk's Learning application, if you want to. Next, the coefficient of variation. And this is the ratio of the standard deviation to the mean. Standard deviation to the mean. It's a ratio, which means we're talking about a fraction. We could write it like this. And as a fraction, you're going to multiply it by 100%, so the CV, or coefficient of variation, is in a percentage format. Use the sigma if you're talking about the population. Use S if you're using the sample. Very simple. Make a note of that on your statistics special notes. And let's see what we've got. Here's one for you to try. You've got some rainfall, and you've got a sample of farms, and you've got a graph coming up, and you've got the mean and standard deviation for set A. Set A, mean, and standard deviation. Notice they're both in inches. This is the mean, and since it was for sample, that means this is x bar, and, oops, excuse me. Yeah, the mean and standard deviation. Since it's a sample, this one's x. So we're going to take s over x bar, and we'll convert that to percent. And we'll do the same thing for data set B. Here's the mean. And here's the standard deviation. Oops, there we go. This x. Do the same thing with it. Which of the graphs has the larger standard deviation compared to its mean? We're doing some comparison. It's not just the standard deviation. How does it compare with the mean of your data? Well, here's data set A. If you missed it, it's for data set A. Notice what it looks like. It has sort of a nice bell-shaped curve. For data set B, it's got also a bell-shaped curve, but it's different. There's A, there's B. What's the difference? Calculate the coefficient of variation for each one of those. For data set A, you've got a coefficient of variation of 28.9. Second one, 36.7. So that means data set B has a larger standard deviation compared to its mean. Next, we're going to talk about the empirical rule. The three numbers to remember are the ones above: 68%, 95%, 99.7%. You want to remember those two. What they mean is a little bit of this. We'll have a picture coming up too. But here's your standard bell curve. If you've got something that's normally distributed, it's got a bell-shaped distribution. Here's the mean right in the center. And of course, it's also the mode, but that's different. So here's the mean, mu. Now what this says is you've got lots of data. Half of the data are on this side, half of the data are on this side. That's a good thing to remember. This says 68% are within one standard deviation. On the picture, what does that mean? Well, whatever the standard deviation is, go to the left one standard deviation and go to the right one standard deviation. That takes you here, takes you here, and what this says is, with a bell-shaped distribution, 68% of all the data fall within those two. 68% of the data are here, which means 32% fall in this area or this area. So what does the 95% mean? Well, it's something similar. Let's draw another bell-shaped curve. We've got the mean in the center, but this time we're going to go 2 standard deviations in both directions. Twice as far. So how much data is between those marks? Well, 95%. Because we've taken a wider spread, more of our data is in there. In fact, 19 out of every 20 items is going to be within 2 standard deviations. That's 95%. So you might get an idea about this one. So there's a bell-shaped curve. There's the mean in the center. This time we're going to go 3 standard deviations in both directions. It's going to cover even more of the data. In fact, 99.7% of the data will be within 3 standard deviations to the right or 3 standard deviations to the left. In other words, there's going to be very few data items that are that far away from the mean. That is the empirical rule for bell-shaped distributions. Keep in mind, this is only for bell-shaped distributions. If you've got a distribution that looks like this, you can't use the empirical rule. If you have a distribution that looks like this, that is not a bell-shaped distribution, forget about the empirical rule. Next, if you're a basketball fan, you might ask your grandparents about Wilt Chamberlain. In 1961, he won the rebounding title with 27 rebounds per game. Even now, that would be quite amazing. He was one of the first 7-foot centers in the NBA. So, read through that. And when you're ready to move on, unpause it again. So what can we do with the empirical rule? Okay, first of all, you notice we're talking about a distribution of weights. And notice it's bell-shaped. That means we can use the empirical rule. Now, first thing I'm going to do is, since it says there's a mean of 3,000, mean equals 3,000 grams. So I'm going to write that down here so I don't have to keep looking up there and pull it out. They've also got a standard deviation of 500 grams. Now, we've got some questions. The first question is, what percentage weigh between 2,000 and 4,000 grams? You might start by drawing a picture. Here's a picture. The mean is in the middle, 3,000 grams. So imagine a 3,000 gram baby. So what is that? If you want to know, it's about 6.6 pounds. If you're curious, and the standard deviation is about 1/2 of a kilogram, or somewhere around a pound. Now it says, what percentage weigh between 2,000 and 4,000 pounds? Well, the standard deviation is 500 grams, and we're talking about 2,000 grams here, and 4,000 grams there. How far away is that? From here to here is 1,000 grams. So what we need to ask ourselves first is, how many standard deviations is that? Well, the standard deviation is 500 grams, so we're talking about 2 standard deviations. 500 times 2 is 1,000. On the other side, we're still talking about 1,000 grams from 3,000 down to 2,000. Oops, one more zero there. There we go. And that also corresponds to 2 standard deviations. 2 standard deviations, bingo, we've got it. 2 standard deviations both ways, and we're talking about 95% of the babies weigh between 2,000 and 4,000 grams. 95%. That's because there's 2 standard deviations both ways. Got that? Okay. Since we've finished that, we'll check that off. And we'll look at the second question. What percentage of newborn babies weigh less than 3,500 grams? Well, again, we'll draw a picture. Not a very good picture apparently, but we'll stick with it. Our 3,000 grams is right in the middle. And we're interested in something about 3,500. 3,500 is something like this. And we're interested in what percentage, is less. I have to redraw that. Scratch that. Here's our new picture. It looks a little better anyway. So here's 3,000 grams at the center. And here's our 3,500 grams. And we want what is less than 3,500 grams. Well, there's a couple of different ways of doing that. One way is to look at it like this. The 3,000 here, the 3,500 there. And notice that's 1 standard deviation away. 1 standard deviation this way. And that's important because if I look at 1 standard deviation in the other direction, this part right here is 68%. So, how much do we have just in this part right here? Remember, we want everything from 3,500 down. We already know that from here on down is 50%. If we can figure out what that is, then we can add it to the 50%. Well, 68% are between here and here. 68%. This part right here that I've colored in is half of that. So this part right here is 34%. And this part is 34%. We've got 1/2 of it to the left. So together, we've got 84% of the babies are less than 3,500 grams. Now, if you backtrack just a second and think about it, 3,000 was the average. 3,500 is heavier. So we're talking about babies that are a little bit on the heavy side, but normal, all the way down to as small as they come. 84% should make sense. 50% over here, plus another 34% there. So most of the babies are less than 3,500 grams when they're born. Now the last part I've got so much there that I'm going to clear this. So, erase all ink on this slide. There we go. So we're going to attack the third question. It says calculate the range of birth weights that would contain the middle 68%. Again, I've got a picture. Middle 68%. 68%, that means we've got, here's the 3,000, and 68% means one standard deviation this way and one standard deviation that way. What would the weight be? Well, one standard deviation is 500 grams. So we're talking about 500 grams this way. That's 3,500 grams for that baby. And the lowest one we're interested in for the 68% would also be one standard deviation away, which would be 2,500. That's the 3,000 minus the 500 for the one standard deviation. So, the range of birth weights would be the middle 68%, one standard deviation both ways would be 2,500 grams to 3,500 grams. And there's our answer for the last one. All right, moving along. You can go through this if you like. We've just covered most of that. If you like the looks of this better, that's fine. So, these weights lie 2 standard deviations above and below the mean. According to the empirical rule, 2 standard deviations means 95% between those two. So we can say that 95% of the newborn babies weigh between 2,000, that's 2 standard deviations away from 3,000, and 4,000, 2 standard deviations above the mean. This is important information for a doctor to know because they have to use different approaches for babies measuring real low or real high in the range of weights, birth weights. There we go. And there's our 84% that we got earlier. And that's a good picture of what we did. Their picture is a little bit better than mine. I'm not complaining. And let's see. All right. The important thing you need to know about Chebyshev's theorem is that we're not going to do it. You can ignore it entirely. And I think that just about takes us to the end. Oh, no, sorry. Okay, so with one more item. It says calculate the standard deviation for the frequency distribution of the final grades in the table below. So how do you do that? Well, number one, we probably tried to forget about this, or by accident. We don't have the actual grades. What do we do if we don't actually have the grades? We get the midpoint for each one of those. So add those two together, divide by 2, the midpoint is 96. Add those two together, with the midpoint, 87. Next midpoint, 78, and then 69 and 60. So what are we doing? We don't have the actual grades, we only have the frequency distribution. Since we've got 4 grades, they're somewhere between 92 and 100 and we don't know where they are, we're going to assume that all 4 of those grades are 96s, right in the middle. And we're going to assume that all 12 of these grades are 87s. It's our best guess. So what we're going to do is, in our calculators, we're going to put these items in L1. L1 will contain 96, 87, 78, 69, 60. Right across from them, for example, L1 will have 96 on the top. In L2, we're going to fill that as well, but with frequencies. So 96 has 4 items, 87 has 12, and so on. Once you've got those numbers in, and double check. Because if any of those numbers is wrong, the whole thing is shot. So double check, please. Once you've got those numbers in, then you know how to do the calculations. You go to Stat, and you go to one variable stats, and for the list, you're going to put L1, and then something a little bit different. For the frequency list, you are going to put something in this time. And then you can go down here to calculate, hit enter, and you get your information. You get your standard deviations along with a lot of other things. Of course, you don't need to do all that. The calculator makes it very easy. You could even do the same thing with Excel, I'm sure. I haven't tried it, but I'm very confident that you could do that. Those would be some of the things you would do, and not doing them. The calculator is taking care of that whole thing, so we can concentrate on the concepts and not the actual grinding calculations. Here's another one. Give this a shot. We've already gone through one example. Notice that what we have is a frequency distribution. It doesn't say that, but we've got the group K for a frequency distribution. What are we going to put here? You should get that by now. You're going to put those midpoints in L1, midpoints in L2, and go through the same process. And if you want a tiny challenge, you could put those in L3 and these in L4 and just do the same thing, just using different lists. Just a small challenge, a very small one. Unnecessary, but you could try it. That's a challenge to see whether you really know how to do the calculator or whether you're stuck on L1 and L2 all the time. And of course you could do this, but I think we would have you committed if you actually did all of this by hand. You can see how much trouble that would be. Even if you were using a real cheap calculator, this would take a lot of time. And we've come to the end, folks. I hope you've enjoyed our trip on measures of dispersion. See you next in 3.3. Bye for now.